Hi, my name is Usama Al-Qaid, and this is a presentation of a transistor-level relational semantics for electrical road checking by SMT solving. It's a joint work between the Verimag Research Lab, the LIP Research Lab, and Aniah, a company that develops verification tools for integrated circuits. At first, I will start by introducing the context of this work, and let's have a look at a simplified circuit design flow. Consider we have a circuit designer which writes a circuit description in some hardware description language. Such hardware description can be automatically synthesized into logic gates. If we go one abstraction level below, we can actually view the transistor level schematic that is associated with it. And this schematic is described by a netlist. In a typical design flow, there might have some other designer that edits the already generated netlists or even creates new ones. When combined with power information, we can go further in the design process up to layout generation and follow multiple other steps all the way to the physical implementation. Each of these abstraction levels is subject to verification. There's, for example, functional verification, which is often associated with the register transfer level. At transistor level, we talk more about electrical verification, and at the layout level, we may perform layout versus schematic checks, for example. But it's only the electrical verification that fits within the scope of this work. We address the problem of transistor level electrical road checking. The goal is to check whether integrated circuits are compliant with some design properties, and our approach consists in defining transistor level circuit semantics that is voltage aware in the sense that it is able to handle multi-supply designs, topology agnostic, conservative with respect to voltage drop quantities across electrical paths, and that is able to capture steady-state circuit configurations. We are going to use SMT solving to check specific properties. SMT here refers to Satisfiability Modulo Theories. In other words, we write a logical formula with booleans and numbers, and we use some SMT solver to check whether it is satisfiable. The motivation behind this work is to apply formal verification techniques in the context of electric circuit verification and improve analysis completeness compared to existing techniques. I will now introduce some basics about transistors. We distinguish two transistor types. Both have a gate, source, and drain nets, where the voltage applied to the gate controls the connection between source and drain nets. For the NMOS type, the current from source to drain increases as the voltage difference between the gate and source increases. But when such a voltage difference is lower than a certain threshold, the current is null. It is very common to consider the NMOS as a switch that is either turned on or off with no intermediate state. The red curve shows such abstraction. The PMOS type, on the other hand, is complementary to the NMOS, and similarly, we consider the switch abstraction as a simple way to model its behavior. In our modeling, we adopt the switch abstraction rather than the real behavior. Let's now get into the details of a local relational semantics. In this part, we are going to keep this inverter circuit so that we illustrate the different ideas on it. First, we define the structural information of a circuit. These are the nets of the circuits. Some of the nets are special, for example, supplies and inputs. In addition, we distinguish two device sets, one set for PMOS devices and another for NMOS devices. We can apply some functions on devices to retrieve the nets they are connected to. These are transistor gates, drains, and sources. The second type of information is circuit state information. We define a voltage function called V, which maps every net to a rational value representing its voltage value. We also define a predicate called on, which tells for any device whether or not it is turned on. We will see in a while how both function V and predicate on are constrained. Let's first start with the rule that constrains transistor states. This rule says that for every device Mx in the set of NMOS devices, the predicate on of Mx is true if and only if the voltage of the gate is greater than the voltage of the source, or if the voltage of the gate is greater than the voltage of the drain. That is because source and drain can be used interchangeably since their physical structure is basically the same. A similar rule is defined for PMOS devices where the predicate on is true if and only if the gate voltage is less than either the source or drain voltage. Before we move to the next rules, there is an important notion I would like to introduce. We call this the static net neighbors. A net may reach some other net through some device. We use the triple notation for that, and I will show examples on the inverter. The net Z has two neighbors since it corresponds to a connection of two devices. Device M1 through which it can reach VDD, and device M2 through which it can reach GND. VDD can reach Z through M1, and GND can reach Z through M2. Input A, however, has no neighbors. Now, back to the semantics rules. This rule constrains the voltage of every net in a local manner. It only applies to the nets that can somehow be inferred from the state of the circuit, but not the ones forced by the environment, so supplies and inputs are not concerned by this rule. For a given net n, the equivalence in this formula states that the voltage is greater than some neighboring net if and only if it is also less than some other net. In other words, the current is flowing through the net if and only if current flows in and out of the net. If the current doesn't flow, then the voltage is equal among all connected nets, unless when all the neighboring devices are off, in that case the net is floating. On a circuit level, this rule ensures that the voltage values are strictly monotonic on any active electrical path. Let's now apply this rule to net Z of the inverter and see when it is satisfied. We notice that the net Z has two neighboring devices, M1 and M2. If the two devices are turned on, the rule can basically be satisfied in two cases. The first is when the voltage of GND is less than the voltage of Z, that is less than the voltage of VDD, and this case is coherent. The second case is when Z is situated between GND and VDD, but when the order is not coherent with the supply values, so it's impossible to happen. The rule is also satisfied by having only the device M1 to be turned on. The voltage of Z can only be equal to the one of VDD. This corresponds to a normal functioning of the inverter. Similarly, when only M2 is on, Z connects to GND, and that too is a normal functioning of the inverter. The last rule I will introduce is for the static voltage range. It only applies on nets that are neither supplies nor inputs, and it constrains the voltage of a given net to be bounded by the minimum and maximum voltages of the supplies that the net can possibly reach. The reachable supplies of a net is the power set of the set of supplies, and this information can be obtained from a static voltage propagation algorithm. For example, the reachable supplies from net Z of the inverter are VDD and GND, while the input A reaches no supply. We can now combine the constraints we have defined to build a circuit formula. We denote the circuit formula by F, and we define it as the conjunction of the semantics rules. We may also combine it with additional rules to specify constraints on supplies and inputs. For example, we may directly assign a voltage value to each supply and specify input values. The formula of the circuit can therefore be used to check specific properties using some existing SMT solver. We conducted a case study on the problem of missile level shifters. A level shifter is a circuit that is used to translate voltages from one power domain to another. On the following example, we say there is a missile level shifter between two circuits when these two circuits have a direct connection while having different supplies. In such configuration, a level shifter is needed. The detection of missile level shifters is a well-known problem in circuit verification. Some classical analysis techniques consist in performing static voltage propagation to check whether a device can possibly reach different supplies. This technique is infamous for raising lots of false alarms, so people tend to complement static voltage propagation with pattern matching in order to reduce the number of false alarms. Pattern matching refers to comparing circuit topologies against already known level shifter patterns and eliminate raised warnings on that basis. This category of techniques remains limited because false alarms can still go unnoticed due to the non-exhaustiveness of known level shifter patterns. And this is where our method comes into play. We express the missile level shifter error directly in our model, and we check whether a device can actually be connected to different power supplies. In fact, the direct consequence of a missile level shifter is the undesired current it causes through devices that are at the interface between power domains. This happens when a device is turned on with a voltage difference between its source and drain nets, which inevitably causes the current leakage. What we propose is to build a corresponding error formula in terms of the variables that we already use to encode the formula of the circuit. We denote the error formula as the missile level shifter error on a device MX. The error is true if and only if the concerned device is on and when there is a voltage difference between its source and drain nets, and when the voltage applied on the gate is greater than the minimum reachable supply from source and drain, which is usually the ground. We can also build the error formula to express the existence of a missile level shifter within the circuit, which can be formulated as the disjunction of the error formulas expressed each for a device. We implemented a verification tool in the OCaml programming language, and here is the verification methodology we use in our tool. It has been specified here for the missile level shifter error, but it is the same for other errors. We encode the circuit netlist into a formula using the defined semantics. We encode the error using variables of the circuit formula. Then we ask a solver to check whether the conjunction between the circuit formula and the error formula is satisfiable. If so, we conclude that it is indeed an error, otherwise it's not. We use this process to analyze large industrial circuits. Analyzed circuits are part of a 10-bit analog to digital converter. They represent a large variety of circuit topologies. The top-level circuit is made of more than 200 million transistors, where 20 distinct power supplies are used, and where more than 11,000 instances are analyzed. Each instance corresponds to a circuit that is used with a specific power configuration. This plot shows the time that is spent by the solver to check the satisfiability of formulas. Every dot on the plot corresponds to a circuit instance. These results show that the presented verification approach scales very well and can analyze circuits of the order of 1,000 transistors just in a few seconds. Future work include studying the applicability of classical techniques for scaling up, developing technology-aware semantics that takes into account physical device parameters, and improving the transistor modeling to be less abstract for more quantitative results.